Good evening, everybody. Hopefully, we've got some returners. So you've heard this a little bit before, and hopefully we've got some new folk connected in. So my name's Brian Lawson. I'm the technical director for Projex Solutions. We're a project management and engineering services company based in West Yorkshire. We also have an office up in sunny Teesside as well. We're hosting these lectures in support of the West Yorkshire Area IMechE committee, and as well as that, this series of lectures have been run in collaboration with the University of Huddersfield. So thanks to Josh and Carl from the engineering department at the University of Huddersfield. This is the 6th in a series of 8. Hopefully I've got my maths right this week. And it's entitled "Improving the Quality of Steam." The lectures are aired over Teams, presented by Dan Wells, who's the National Consultant Specialist for Spirax Sarco Limited. In a moment, I'll hand over to Dan. Just some very basic logistics. The presentation as we go through the lecture, and if it's appropriate, I'll throw the question in there. If not, we'll keep it till the end. So where did I get to on my list? Well, actually, I got to the bit where it says over to you, Dan. So it's over to you, buddy. Take it away.
Great. Thank you very much for that introduction, Brian. And thanks as always to Projex Solutions, IMechE West Yorkshire and the University of Huddersfield, without which these series of presentations wouldn't be possible. So just really to move forward with that, Brian, we've obviously introduced Spirax Sarco in some considerable detail in the previous presentations we've gone through. So I'm not going to do that to death. I'd just like to cover off that Spirax, as a group of organisations, we're not specifically all about steam. I do work for the Steam Solutions division, but moving forwards, as we go through the future presentations in this series, we will start to introduce those different solutions and concepts we have to demonstrate how we can help our clients generate steam from an alternative source of energy, such as natural gas. And of course, we've introduced Spirax Sarco in the UK and Ireland in some considerable detail. I'm not going to bang that drum too much. Suffice to say that we do have a really useful suite of resources, calculators and configurators that you can access on our website that can help you with any and all aspect of steam engineering. So, as Brian's mentioned, this is a series of presentations. So we have covered off the fundamentals. We've covered off the things that we need to do to employ best practice, not just in how we generate the steam and distribute the steam, but we've also looked at concepts such as good practice with steam trapping. We've looked at steam heat exchange. Last week, we looked at steam management. And today, I really want to move away from the energy side of steam engineering. And I really want to look at the causes and consequences of generating, distributing, and more importantly, using a condition of steam that isn't as it should be. And as far as today's presentation is concerned, I've chosen to specifically drill down and look at the food and beverage industry in some considerable detail. So please do bear in mind that a lot of what we're going to learn in today's webinar, it is applicable to other industries such as the pharmaceutical sector, healthcare sector, chemical sector, essentially to help us understand that we need to think about steam as being so much more than just a utility. Whenever we think of a utility like gas or electricity, for example, we take for granted that it's going to be consistent. And hopefully, having sat through those previous presentations, you'll have realised that steam is not consistent. It is going to exist at different pressures, different temperatures. Sometimes it can be wet, other times it can have air and other non-condensable gases present. And of course, it can and will carry contaminant from time to time. So I'm going to drill down today, and I'm really going to focus on how a less than consistent or inadequate quality of steam, it can really impact the food and beverage sector in particular. So when we're talking about steam, we need to remember that for the vast majority of applications, that steam will be used for its thermal energy attributes, which essentially means we're using the steam to heat something up, to cook something. So there are a lot of different applications. There are a lot of different processes where we can use steam. And there are far too many applications for me to go through in detail today. So what I've really done is I've just picked out a few key areas where we can use the steam. So hot water heat exchangers, whenever we're producing steam for hot water, or whenever we're using the steam to heat something up, it doesn't have to be water on the secondary side. You know, it could be orange juice, it could be dairy products, it could be anything really. Now, the things to bear in mind for heat exchange, as we've covered off in previous presentations, is we need to make sure that the steam arrives at the point of heat exchange at the correct mass flow, the correct pressure, and the correct temperature. And we also appreciate that whenever we use steam for heat exchange, the byproduct is condensate. So not only do we need to think about how we get in the steam onto the process, we need to think about how we're getting the condensate away. Because if we're not getting the condensate away at the appropriate rate, the risk is that condensate could back up, it could flood the heat exchanger, we've got a barrier to heat exchange, and we're no longer heating the product to the appropriate set point temperature or in the appropriate time. Taking that forward, jacketed vessels are very commonly used in the food and beverage sector for cooking soups, sauces, jams, for example. So you can see on the image towards the left-hand side of the screen, the space in red, that's the steam that really heats the product up. It doesn't come into contact with the product that is shown in green. So again, we need to think about how we control the mass flow rate and then the pressure and temperature of the steam. We need to think about those temperature gauges because that's going to tell us the temperature of the steam that we have to work with. We need to vent the air away because we appreciate from those previous presentations we've gone through that air is a barrier to heat exchange. So if we haven't allowed for the venting of that air, then we could have an insulating bubble, an insulating film of air that prevents the steam from seeing the entirety of the heat exchanger. And that in turn could mean that we're getting more heat energy passed to one side of the jacketed vessel than the other. So we're going to get an inconsistency to heat transfer. We might not be heating the product up at the appropriate rate or to the appropriate temperature. We could have product burn on, product spoilage. And that in turn could result in an increase in CIP cleaning costs. And it also means that we need to get rid of the condensate from the bottom of the heat exchanger, or the jacket vessel in this case. Retorts, commonly used in a lot of industries where we may be cooking or pasteurizing a product in a tin. So it could be a can of lager, it could be a tin of baked beans. The product is sealed within the pouch or within the container. So we're probably putting a forklift truck of cans into a retort. We close the door of the retort, we introduce the steam, and we bring it up to the appropriate pressure and temperature. So the steam's not coming into contact with the product itself, but again, it's vitally important that we get the correct mass, the correct pressure, and the correct temperature of steam. So again, as with those other heat exchangers, it's really important that we get the air and the other non-condensable gases away because they're a barrier to heat exchange. And we need to get that condensate away. Remembering that condensate as a liquid, it's high temperature hot water. It's going to exist at the same temperature as the steam. It's just got far less energy than the steam has. So it needs to be considered a byproduct. And CIP, we know that we consume a significant amount of steam for CIP purposes to elevate the temperature of those caustics, acids, the rinsing agents. And that's regardless of whether it's a once-through CIP system or a CIP system that could be recovering some of the rinsing agents. So of course it means that if we've got a significant demand for CIP, for example, if we've got those jacketed vessels where we're not employing best practice and we've got a bit of product burn on, not only are we likely to have a higher cost of the product itself and a greater risk of inconsistency and product spoilage, it means that our CIP costs could be significantly greater as well. Pasteurization in this country, it's far more popular to have a closed loop pasteurization system, which means the steam isn't going to come into direct contact with the product itself. But of course, we know that we need to heat the product on the secondary side up to a very, very critical set point temperature in a critical period of time. So it makes it all the more important that the steam exists at a good condition or quality in order for us to do that efficiently, quickly, and without an unnecessary burden of energy to generate that steam. Evaporization, we know that we evaporate certain products to concentrate them, to drive off the moisture content. A good example would be orange juice, for example. So by driving off the moisture content, the packaging and transportation costs are going to be greatly reduced. So evaporators generally work in multi-stages. You can see over at the left-hand side of the screen, we've got a single phase evaporator. And over at the right-hand side, that's a two-phase evaporator. The rule of thumb is the more stages we add, that the more efficient that process actually becomes, because we use the vapor as the energy that is driven off one stage to give us a head start in elevating the temperature on any future stages. But again, the steam isn't coming into contact with the process. So it means that it's important that we think about the condition of steam, the mass, the pressure, the temperature, and to make sure it's got no air or other non-condensable gases, and that we're getting rid of the condensate at the appropriate rate so it's not backing up and becoming a barrier to heat exchange. And then moving forwards, we need to think that there are also going to be processes such as humidification. And I'm using humidification as an example. We're showing a bread oven here. We're humidifying the oven so that bread's got a nice golden sheen on it. But we also humidify pasta, pizza dough. We will humidify cheeses. We'll humidify tomatoes, bananas, avocados, and so forth. The thing to bear in mind is we need to introduce the steam onto the process at the correct mass flow rate, pressure, and temperature. But unlike a closed system, like a heat exchanger, the steam and also the condensate, it becomes part of the process. It becomes part of the product. So simply put, there isn't any condensate to recover. The steam becomes an ingredient. Another ways that steam could be considered an ingredient. If we're using steam for sterilizing, it could be sterilizing a can or a jar or a bottle. Anything that the steam is carrying is going to become part of that process. So of course, we're moving further and further away from the requirement to think of steam as a utility towards the point where we really need to think of steam as an ingredient. Steam is a fantastic carrier of heat energy, but it carries other things as well. As we know from those previous presentations, that steam, it can and it will carry an excess of moisture. That moisture is chemically conditioned, and it can carry rust and scale and other particulates. Now, what's increasing in popularity, especially in Scandinavia and Northern Europe, is what we call steam infusion. Now, if you think about that jacketed vessel that we spoke about previously, we're cooking the product, the sauce, the soup, the jam. We're cooking the product from the outside in. and the steam is not coming into contact with the product. Now, if we took a lance, a steam lance, and we dropped it straight into the soup or sauce or jam, and then we introduced steam, then we'd be cooking the product from the inside out. That's going to give us a number of what may be benefits to the client. For example, by introducing steam straight into the product, then the steam's going to have a macerating effect. It's going to make a very smooth consistency for that soup or sauce or jam. The steam is going to elevate the temperature of the process very, very quickly, so we can get a very rapid throughput of product as well. It means that it's easier to control the temperature of the process. It also means that the steam is going to hydrate the product. We're going to add some moisture to it as well. But it also means by cooking the product from the inside out, it means we've minimized that risk of any product burn on, which means we've driven down the CIP cleaning costs as well. So steam infusion is something that has been very, very well received by a number of processors in different environments. Another key difference between steam infusion and jacketed vessel cooking is that when we're cooking through steam infusion, the steam itself is going to be an ingredient, and therefore anything that the steam is carrying will also become an ingredient. Whereas that's not the case whenever we're heating a process up using a jacketed vessel. So this terminology that we want to address, whenever we're talking to a client that's operating within the food, beverage, maybe even the pharmaceutical and potentially the healthcare sector, the terminology that is commonly used is steam quality. What's your steam quality like? The vast majority of clients, they won't really have an understanding of the steam quality that they have all of the time. So we want to ask a few questions. And the first thing that we do when we're talking about steam quality is we break it down into two different areas. So the first area is what we call the thermodynamic properties. Think of it as the physical properties of the steam. How dry is the steam? How much air and other non-condensable gases are present in the steam? How much superheat does the steam have? And the next thing that we need to give thought to is the purity of the steam. And as we've mentioned, the steam can, we need to think of the steam as an ingredient. It can have a very, very high energy content. It's a fantastic carrier of heat energy, but it can carry other things as well. So for that reason, we split it into two. The reason being is we can have steam that has got fantastic thermodynamic properties, but it's carrying a lot of contaminants with it. And vice versa, we can have steam that is very, very pure with very, very few contaminants, but it might not be very, very good at doing its job because it might not be carrying too much energy. So we need to think about both at the same time, but for different reasons. So with regards to the thermodynamic properties, there's a standard we can refer to. That standard's called EN285. And EN285, it helps us to measure, it helps us to define the quality of steam that we have. So EN285 states that in order to have compliant steam, that steam needs to be 95% dry. Why? Well, it means that we know exactly how much water there is present within the steam. So we know the extent at which it is going to dilute the process. So we know how much energy is present within the steam. We're also looking for 3.5% of air and non-condensable gases present in a sample of condensed steam. Why? Well, if we've got any more than 3.5%, we're going to have that barrier to heat exchange that we've spoken about in previous webinars. And then finally, we're looking for less than 25-degree superheat to be present within the steam. It's very unlikely that superheat is going to occur in a food and beverage process, but when it does occur, it's got to be taken very, very seriously because superheat, it may sound like a good thing. The reality is that whenever we're using steam for heat exchange purposes, we need the steam to have a very, very slight moisture content because that's the only way that the steam can condense and give up its heat energy. That's the job we need it to do. If the steam is superheated, it's too dry, It's got too much energy, but it can't give that energy up. It's very, very selfish. And it also means that we may be susceptible to a little bit of damage to capital equipment through things such as drywall erosion. So EN285, it helps us to measure and define and understand those thermodynamic properties. The problem is we don't really have a means of measuring or monitoring the purity of the steam, the contamination that is likely to be imparted by the steam. So we could have steam that is EN285 compliant. It's got an excellent energy content. It's very, very dry. It's got very little oxygen and non-condensables, but it could also be carrying a lot of contaminants, which is why we need to think about the thermodynamic properties and the purity in two different ways. So where does that risk of contamination come from? The first thing is, well, it's down to the condition of the water that we're using. And that's going to vary from one client's site to the next. And this really just, we could have a client that has got two factories that are exact mirror, an exact mirror of each other. But one of those factories could be located in an excellent water quality area, and one could be located in an area of very, very poor water quality. So we could be treating that water in different ways and for different reasons, which means that the chemical composition of the water going into the boiler is going to be completely different. And some of those chemicals, I mean, we don't know the chemicals that our client is using because it could be down to the peculiarities of the infrastructure itself, the boiler, or the chemical composition of the water. Even if our client is based in an area that's got excellent water condition, could be that they're using borehole water, or that they're using river water or reclaimed water. So we need to be really clear on the water treatment regime. Now, I can't pronounce half of those chemicals, and I'm not even going to attempt to. But in many cases, our client will say, well, it's okay because I'm using chemicals that they're FDA approved. The food and drink approved. They're suitable for going into the process. The problem we have is the FDA states that those approved chemicals are only going to be approved if the chemicals remain within the boiler, and if they remain within the boiler at the appropriate concentration. And we can't guarantee that, because as we've learned from previous presentations, when the boiler surges to meet that demand for steam, it's highly likely that some of those chemicals can be drawn out of the boiler in wet form. And when we get a high concentration of chemicals within the boiler that results in that foaming layer that we've spoken about previously, we're drawing out an even greater increase of chemicals in foam, which ultimately dries out into scale. And if we're using that steam for direct injection purposes, for humidification, for sterilization, for steam infusion, those boiler chemicals are going to become part of the process. So I've shown this clip previously. This is a typical plant steam boiler. We might be holding 10, 20 tons of water. If we get a sudden demand for steam, we get a fall in pressure. That fall in pressure causes the steam bubbles to expand, and that agitates that high concentration of chemicals. It's going to create a very, very deep foaming layer. And as we've mentioned, just one of the problems with a high concentration of those total dissolved solids, it's that foam that can be drawn out of the boiler along with this foam, along with the steam. So of course we've mentioned that foam is going to create problems with wet steam, which, as we know, means that we're going to have very little energy present within the steam, and we're moving away from that 95% dryness EN285 compliance requirement. But it also means that foam is going to dry out. It's going to form scale. That scale is going to be moved by the steam, maybe at 25, 30, 40 meters a second. At 40 meters a second, it means that scale's moving at 90 miles per hour, which of course means that we're going to get failing components like control valves or flow meters. Now that means it's very, very difficult for us to accurately control the steam that's moving onto the heat exchanger. It means that any foam that is being carried by the steam is going to create a barrier to heat exchange. That scale is going to prevent the steam from heating the process up efficiently and at the appropriate rate. But worse still, when we're using the steam directly, that high concentration of boiler chemicals, which are completely unpronounceable to me, they're going to be an ingredient. They're going to become part of the process. Now, what I'm showing here, hopefully it really emphasizes that point that we're making. If we condense a sample of the steam, if we change the steam from a gas to that liquid condensate, any contaminants that are present within the steam are going to be retained within that liquid condensate. So you can see straight away visually, you can see the sample of that condensate over in those two bottles over at the left-hand side of the screen. You can see that it's not fit for drinking. You wouldn't pick that bottle up and drink it. So why would you accept the fact that it could become an ingredient and could become part of the process? I think very, very few people would accept that if they were made aware of that risk. So it really comes down to understanding what's driving steam quality. Well, there are a couple of regulations in practice that are not too commonly understood, or that they're not necessarily of a heightened level of awareness in the vast majority of food and beverage plants. One of which is what we call EC1935, and that really looks in some detail at processes that come into contact with food. So that could be, for example, conveyor belts that are moving finished product, foodstuffs around a factory. Well, the conveyor belt is going to come into contact with the product, so of course that needs to be regulated. And EC1935 has now started to understand that, well, in many processes, steam is also going to come into contact with a process. So it could be the steam that is being used for generating CIP agents. It could be, if we're using steam for SIP purposes, humidification, sterilization. So steam can come into contact with a product either directly as an ingredient. For example, if we're injecting the steam through steam infusion, or indirectly, if we're using the steam to sterilize capital equipment, or even sterilize containers, pouches, jars, cans, for example. So there are a lot of different processes. Again, too many processes for us to list, where steam will come into direct contact with a product or an atmosphere. In other words, whenever we're working on a process such as this, should we perhaps be thinking of steam as being more than a utility? Shouldn't we be thinking of steam as being an ingredient? Well, here's another example for you. Let's take an example of, let's say our client is producing tomato soup, and let's say they've made the decision to move away from cooking tomato soup in a jacketed vessel, and instead they're going to move towards steam infusion for reasons we've gone through previously. Well, the process might dictate that we take 60% tomatoes, we add 20% potable water. Now, we know we need to use potable water because it's food, it's water that is going to be an ingredient. Of course, it's highly regulated. And then we want to add 20% steam, because of course we know that when steam condenses, it changes state from gas to that liquid water. So that might be what the process dictates. But if we looked on the ingredient label of that can of tomato soup, it'd invariably say 60% tomatoes, 40% water. But we need to remember that the steam isn't necessarily just water, it's chemically conditioned water. It's going to have that rust, that scale, and any of those boiler chemicals that we find it very, very difficult to regulate for reasons we've gone through. they are going to become part of the process. So it's vitally important that if our client is very, very closely regulating and monitoring the condition of water that they're putting into the process, well, the steam needs to be considered in exactly the same way. So if we're thinking about a major multinational corporation, they could be manufacturing a product, and it's highly likely that product is going to have a premium variant. For example, it could well be that our client is producing soup that is organic, it's guaranteed organic, or that soup is guaranteed halal or guaranteed kosher, or it's guaranteed it's going to be free of gluten, or it's got guaranteed free of any other ingredients or processors. It really means that if we're making those guarantees, the consumer's got an expectation that they've got a premium brand. And the reality is that our client could be buying that kosher, halal, organic soup. It means that the tomatoes are certainly meeting that requirement. But what about those boiler chemicals that we're putting into it? So I think it was around about this time 2 years ago, 2022, there was some legislation passed in the UK Parliament called Natasha's Law. And Natasha's Law was brought in front of Parliament down to a young girl that unfortunately had an allergic reaction to a sandwich she'd purchased, and she sadly died. And Natasha's Law stated that ingredients had to be correctly identified on the packaging. Well, where does it say steam on an ingredient label? It doesn't. It says water. And that's not the case, because it isn't even a good condition of water. It's carrying God knows what. It's carrying chemicals, rust, boiler scale. So it really stands to reason that if we want to stand by Natasha's Law, and if we want to stand by the integrity of our product, we need to generate, distribute, and ensure that that steam reaches the process at the appropriate condition. So let's have a look at where that risk of contamination comes from. It's the quality of the water that we're using. It's how we chemically condition that water. We need to make sure that the chemical dosing pumps are correctly calibrated. I mean, the part of the UK where I live, the water quality can be drawn from different reservoirs and different aquifers at different rates and at different parts of the week. We can be bringing water from the Pennines. We can be bringing water from the Lake District or North Wales. And that chemical composition is going to differ. So that makes it very, very difficult to know the condition of the water and its chemical dosing regime. So, of course, it makes it very, very difficult to ensure that we're not getting the chemicals drawn out of the boiler in wet form or drawn out of the boiler as that high concentration of foam and carryover. We can have a buildup of pipe scale over time. We can have corroding pipework if we're moving the steam from a plant steam boiler, carbon steel, in a carbon steel infrastructure. And if we're moving that steam thousands of meters around site, for reasons we've gone through in previous presentations, we understand how that steam can start to condense and get progressively wetter. So by the time we get the steam to the heat exchanger or to the point of use, very, very difficult to guarantee it's of a condition that will meet the requirements of BSEN285 and won't have any impurities present within it. And we know that a lot of our clients, they'll be using steam for different applications and processes. Could be that one of those processes, one of those heat exchangers where the steam is not coming into contact with the product, we could be concentrating orange juice, for example. If we've got a pinhole in heat exchanger, the product, the orange juice on the secondary side, could find itself being brought into the condensate and traveling all the way back from the process to the hot well. The hot well is then feeding the boiler with contaminated water, and therefore we've got contaminated steam moving to the process that is looking to use that steam directly. So the contamination can come from a lot of different areas. So hopefully you can appreciate that plant steam that we've spoken about and that we've covered off in some detail in those previous presentations, it's not always going to be fit for use. On many occasions, it'll be perfectly adequate. We just need to make sure that we don't have too much scale or rust, and that it's dry enough so that we don't have an inefficiency or mechanical issues. But if we're using the steam indirectly, there won't be that risk of contamination. But if we are using the steam directly, we need to think of steam as an ingredient. So if you went onto a steam using site in the food and beverage sector, if you wanted to go into the production area, they'd doubtlessly ask you if you could gown up, if you could wear hygienic coverings, put the hairnet on, and so forth. And if you were to ask your host why, he'd probably look at you like you were crazy. He'd say, well, we don't have any appetite for risk. We don't want you to contaminate the product or the process. And if you were to ask him what that risk was, he'd probably say, well, it's a fraction of a %, but with no appetite for risk whatsoever. But if they don't have any appetite for risk, then surely the host should appreciate the fact that the contaminants within the steam, they pass a far greater risk to the process. And therefore, if the client has applied a HACCP to the risk of the visitor contaminating the process, it should really apply the same HACCP to the condition of the steam. And the only way that it can do that is by referring to the steam quality triangle. So looking at the steam quality triangle, you'll recall that if there's no risk of the steam coming into contact with the process, there's no risk. Plant steam is perfectly acceptable. But for certain processes, steam will come into contact with an application or an environment. And you'll notice that we're talking about filtered steam here. Filtered steam is becoming less and less popular in the UK. And the reason is a steam filter is essentially, it's a mechanical barrier. So we've got a 316 stainless steel housing. We've got a 316 stainless steel sintered metallic element. It is a mechanical barrier. So it will only remove a certain amount of particulate. It won't have any effect on steam dryness, air and non-condensable gases. It won't have any effect on superheat, and it won't have any effect on those chemicals that are in wet form. They will pass straight across that barrier into the process. And in certain cases, they can also cause steam that may exist at a very wet condition to coalesce. And it can agitate air and non-condensable gases out that could create a barrier to steam moving across the filter. So for that reason, we need to install an air vent and a steam trap separately. And of course, they're going to have their own maintenance regime all on their own. And if those traps or air vents, and if the filter itself isn't maintained and repaired correctly, we're not going to get the steam passing on to the process. So wherever we do decide to use a steam filter, then if that filter and if the housing is engineered in 316 stainless steel, then of course everything downstream of the filter itself needs to be engineered out of 316, because if we haven't done so, then we're just reintroducing that risk that carbon steel pipework can corrode and further add iron oxide, rust to the process. And you'll notice that we need a number of other ancillaries upstream of the steam filter in order to ensure that it's at the appropriate condition and we're not really causing that filter to ultimately back up and blind with an excess of rust, dirt, scale, or to have too much of that steam wetting out and coalescing in the filter. It's also important that the filter has got a pressure gauge upstream and downstream to identify when it's starting to block up and when we get a pressure drop. The biggest problem we really have is whenever that filter starts to back up, we've got a restriction to the steam moving to the process. And one of the most common things that the plant operator would do is they would remove the filter. They're getting the mass flow of steam now, they're getting the pressure they need, not getting filtered steam. So it's for that reason, that burden of maintenance and the engineering and the operating issues, it's for that reason that if our client is applying a HACCP, they've identified that they don't have that appetite for risk that filtered steam can bring. So especially when that steam is going to be considered a direct food ingredient, that's when we move up the steam quality triangle. We move beyond that red line and we want to generate what we refer to as clean steam. So clean steam is typically generated by what we call a clean steam generator. And as the name suggests, a clean steam generator, we take that dirty, that plant steam that's got some rust, some scale present within it, and we move it across a second dedicated heat exchanger. And that heat exchanger, it generally works in two passes, as you can see. So we would take high pressure, high temperature steam. That high pressure, high temperature steams come straight from the plant steam boiler. It may have a little bit of rust, a bit of scale, a bit of moisture present within it. Doesn't matter, because that steam is not going to come into contact with the secondary side of the clean steam generator. So all of the wetted parts are manufactured out of 316 stainless steel. On that first pass at the top of the screen, we would fill that with reverse osmosis quality water, for example. If we've got RO water, we're using that high pressure, high temperature steam to elevate that water to about 85, 90 degrees. At that temperature, we've driven off a lot of the oxygen and the non-condensable gases. That water, it now passes to the second pass, and we're using that dirty plant steam again to elevate the temperature of that 85, 90 degree RO water to the point where it can boil off and generate steam. So we've got RO water, which means we've got very, very few particulates, chemicals present within the water. 316 stainless steel infrastructure, we're not adding any boiler chemicals to the water. We've degassed it, we've elevated it to an excellent condition. It's very, very dry. And then we're distributing that steam in a 316 stainless steel infrastructure, relatively short distance, so we know it's not going to degrade and deteriorate. So clients, they would generally have a clean steam generator, a very small steam generator, probably twice the size of a typical office filing cabinet, located very, very close to a process, a point of use. But for larger consumers or for larger requirements for clean steam, it could be a centralized clean steam generator. And that will look very, very similar to the product that we've got on the screen above. It really reminds us that the operating principle is exactly the same. It's just on a bigger scale. And of course, that means that we're likely to be then distributing that steam a much greater distance. So you'll notice I mentioned RO water. The reason we prefer to use RO water is, well, first of all, the vast majority of our clients in the food and beverage sector, they will already have an excellent condition of water on their site. We could potentially use potable water in the clean steam generator. Nothing stopping us from doing that. Remember, the condition of the steam that you get out of the generator, it is going to reflect the quality of the water that you put into it. So there's not going to be any risk or harm of contamination. But the reason we want to use an excellent condition of water going into the clean steam generator is really to protect the integrity of the capital equipment itself. We don't want it scaling up, resulting in a burden of maintenance, for example. So steam traps, steam trapping. We've spoken about steam traps in some considerable detail in the previous presentations. Suffice to say that the steam traps that we use in the infrastructure downstream of the clean steam generator to remove any condensate that exists as a byproduct to that heat exchange in the pipework, It needs to be 316 stainless steel, as do all of the other ancillaries. So we, as Spirax Sarco, we've got a range of products that they're not just 316 stainless steel, but the 316 stainless steel that also happen to be EC1935 compliant. In other words, they're fully certified. So every product, every component within that ancillary, whether it's a steam trap, a control valve, an air vent, they are going to be fully traceable. So it really comes down to the decision of our client with regards to whether they want to adopt those EC1935 principles and have full traceability for all of the components that could potentially be considered food contact materials. So that's an example of one of those EC1935 compliant certificates that we offer. It really comes down to the client itself and what their appetite for risk is. Now, it's important that if we bear in mind those EN285 requirements, we need to understand that on a regular basis, we need to be able to prove that the condition of the steam that is being generated, distributed, and arrives at the point of use is in accordance with the standard to which it's required. So dryness, that's the big one. You'll remember we need the steam to be 95% dry or better. How do we do that? We connect a flask of water at a known temperature and known weight. We connect it to a test elbow. We operate the steam at the design pressure for 5 minutes. We then take the temperature and weigh the water. And if we know its mass and temperature change, we can run a formula that tells us that we know how dry that steam actually is. Now, wet steam is by far and away the most important one for reasons we've gone through. Wet steam not only is a reflection of the energy content of the steam and the likelihood that the steam can create erosion to capital equipment, but wet steam also tells us that we could potentially be diluting the process with too much water. But remember, it's also going to be chemically conditioned water. So we've done a lot of work with regards to wet steam characteristics, what causes it, what the risks are, how it changes in accordance with different velocities and so forth. It really is a topic in itself, but this really is one of the most important points that our client needs to take into account whenever they're working towards not just EN285, but also EC1935 requirements. Air and non-condensable gases, that barrier to heat exchange. How do we test for that? Well, we run the steam, we condense a sample of that steam in a beaker of water. As the steam condenses, it displaces into a measuring cylinder, and any air and non-condensable gases break away inside an upturned funnel. So when we've displaced 100 ml of water from the beaker, we need to look inside the inside the burette to identify how much air and other non-condensable gases have broken away. We're looking for less than 3.5% by volume when we've collected a 100 ml sample of condensate. And then finally, superheat, by far and away the least likely of the issues we're likely to encounter. We measure superheat by, we take the temperature of the steam when it's under pressure, and we take the temperature of the steam when it's let down to atmospheric. And remember, we're looking for a 25-degree differential or less in order for the steam to be compliant with EN285. So when the client is distributing steam centrally, i.e. when the clean steam generator is, 30, 40 meters away from the various points of use, we need to design the infrastructure, not just in stainless steel, but also in compliance with best practice, so we can vent the air away and we can drain any moisture in the form of condensate as a result of that heat loss at the appropriate rate. And at the point of use, we want to ensure that our client can condense a sample periodically. they will generally take responsibility themselves for taking that sample away. They'll take it to the resident food scientists, the microbiologists, who will then run some analysis on that sample, generally by conductivity. That the greater the conductivity of that sample, then the greater the likelihood that it's going to contain some contaminants. Sample coolers are very commonly used around steam systems, but it's important that when we're using it on a clean steam system, it needs to be a hygienic sample cooler. We need to have highly engineered and highly polished surface areas, so it's not the sample cooler itself that is imparting that contamination to the sample. And then finally, if we need to prove the condition of steam that we have, then we need to have the appropriate test points. This is a test point that has been designed and engineered by Spirax Sarco. It allows you to take those 3 EN285 tests on a regular basis. Without those test points, then Spirax Sarco or any other third party will be unable to prove the condition of steam that is available. So the thing to bear in mind here is we want to engineer those test points, not just at the point of use. That's the important one, of course, but we're going to want to engineer those test points at the clean steam generator and in the distribution pipework itself. The steam at the point of use will generally be tested maybe weekly, potentially quarterly in the distribution pipework, and maybe monthly at the clean steam generator. It helps us to determine that steam and the steam system itself is EN285 compliant at all times. Now, the problem we have is that those manual tests that we spoke about, they're like a snapshot. It's like comparing a photograph to a video. Those tests, we may undertake them at 9 o'clock on a Monday morning. We may have an excellent condition of steam that's fully EN285 compliant. 25 minutes later, the boiler conditions and the process demands changed, and we've no longer got the appropriate condition of steam. So it really reminds us that if we've got a requirement for an excellent condition of steam, the only way that we can achieve that, and the only way we can meet the requirements and the demands of not just EN285, but also EC1935, are by applying that HACCP and moving up the steam condition triangle, generating clean steam from a standalone, dedicated clean steam generator. So there's a lot to go through there today, and hopefully it's given you a little bit of, excuse the pun, food for thought, and it really helps us to consider what the impact of a poor condition of steam is, regardless of whether we're using that steam directly or indirectly. And especially when we're using that steam directly, we need to consider it as being, it's more than a utility, it's an ingredient itself. So next week, we're going to move forward and we're going to look at energy and steam. In other words, how we can optimize and improve the overall energy efficiency of an existing steam distribution network. Hope to see you attend that presentation, same time, same place next week. For those of you that are at university, please do take this opportunity to grab a snapshot of the QR code down in the bottom of the screen. It's going to give you details of our year in industry and details of our various graduate placements around the globe. We're always keen to hear from engineers at university, the next generation of Spirax Sarco employees. So if anybody is interested in receiving a PDF or an attendance certificate, please do reach out and drop either myself or Brian a line. Please, if you've got any comments, any feedback, we'd very much appreciate any comments on tonight's presentation on LinkedIn. And please do feel free to dial in and join us at the same time next week. Brian, have we got any questions that have come in on the chat?
Nothing coming on the chat as yet, but I'll sum up what I think I've heard this evening. Dan, as usual, that was absolutely fantastic. It's encouraging to know that Spirax Sarco are there to support practicing engineers like myself and others that are dialed in. It was interesting to hear about some of the hygiene factors. You mentioned pasteurization and closed and open loop and steam infusion, which an interesting concept, and the different properties of steam, thermodynamic versus purity, those two different aspects, and BSEN285 steam quality, and I can't recall hearing drywall corrosion before, so that's interesting. And also the fact that users will put all sorts of different qualities of water into the systems, and usually it has a pretty significant impact on what comes out of a system.
You only get out what you put in, Brian.
Yeah, absolutely.
And I can see that Keith's got a question as well. If we've got time for that,
yeah.
Brian.
Yeah, we'll have. I'm just.
That's great. Can you hear me?
Keith.
Yeah.
Yeah,
we can hear you, Keith.
Thanks, Brian, and thanks, Dan, and thanks for responding today. I obviously missed all the links and everything else, but I'll come back to you. Couple of things, if I can ask a couple of questions. One is one particular unit operation process which you miss on your presentation, which is using direct steam, is in the world of extrusion cooking. So, for instance, people say, what is that? So you've got all your aqua feed for feeding your fish, you got your TVP, you got your pet food, you've got plant proteins, you got your breakfast cereals and your snacks, and all of you would have eaten product with live steam in the preconditioner process and extrusion cooking. So I was asked, and Dan knows, I was asked by the head of centre at Oslo University when we go there to do a presentation for a full week, can we cover steam? And obviously I've asked Dan for some help on this, and it has occurred to me that going around all these process plants, the process operators, etc., are just assuming steam is steam, so they use it, but I don't think they have any awareness about the quality of the steam and everything you presented today. So I was saying to Dan that we'll probably put this on our curriculum because everybody uses steam and we should actually put it on. I also wanted to ask you, are the retailers now getting abreast of this? So is that going to be something that's going to be questioned at audits whereby processors using live steam? So for instance, you've got Biomar who's in Chile, they've got 8 plants, they've got extruders, each extruder's turning out 4,000 tons an hour. You can imagine the tonnage to feed the fish in the whole coast of Chile, which they process and send to America. It is one of those massive industries that are on the blind side of everybody. It just happens. But I was asked questions about extrusion cooking and the use of live steam. And maybe Dan and Brian, I can ask you questions. You can come back to me because I'd like to put this on our curriculum using your presentations. And maybe when you've got characters in these regions, maybe they can come along and do a 40-minute stint or something and talk about steam. Okay.
No, extrusion cooking, Keith, is important, not just because steam can be an ingredient, but if the steam is too dry, is too dry, you're not getting the pellet conditioning. And if it's too wet, then obviously it's likely to be too crumbly. So it's one for a quality issue, but it's also an ingredient. And a lot of the retailers are looking for full traceability of the product. So if Mr. Retailer, I'm going to use the example, Mr. Tesco, Mr. Asda, for example, if they're auditing a manufacturing process, they know that steam is an ingredient. And if the manufacturer is saying, if the manufacturer is saying we have got clean steam, but it's not clear on his terminology, and if the client has actually got filtered steam, and if that steam filter is not in situ within the housing, then Mr. Tesco or Mr. Asda, they will close the process down. And we've seen that happen.
Yeah, I think they'll obviously get difficult, and I think this is what we need to be doing when we're going around the world from Bangkok to Jakarta to South Africa, seeing all these delegates from these companies. I think we have a duty to start making them aware that steam is an ingredient and treat it with a little bit more respect. And I think they're using plant steam as opposed to a clean steam generator, and maybe they need to reconsider that. So it's taking your message in the world of extrusion cooking, but I will need some help from you, Dan and Brian, to help me with some information that I can present and share. But I thought the presentation was excellent, and it was quite obvious. I went to Denmark last week to two particular companies, and they had an issue with their preconditioner. The preconditioner is where you put live steam in, and they had an issue with that, and it caused a problem with the extrusion cooking process and the final product. So it is important. So I just wanted to say I need to talk to you about the application of extrusion cooking and see if you can help me out in terms of our education to all these companies.
Yeah, we can do that. That's no problem at all, Keith. Please reach out to me directly, and I'll support you with that.
That's lovely. Thanks ever so much. Thank you. That's my question. Thanks.
Thank you.
Okay. Thanks, Keith. So just checking the time, we're a couple of minutes past 7, and currently all you guys connected in are between me and my lamb shank that's waiting in the kitchen. So hopefully we'll see you all next week. Thanks again, Dan. It's another fantastic lecture. The next one is optimizing existing systems, Tuesday the 29th at 6 p.m. and I'll talk to them. There's a couple of messages came in, certainly one saying, can you send me a PDF? Can I leave that with you, Dan? PDF letter of attendance.
Providing I don't have the attendees direct email addresses.
Right, okay.
So if you can drop me a message, on LinkedIn or get your email address to me some other way, I will take care of that. No problem.
Cool. Thanks for that. Thanks for that, Dan. So have a lovely evening, everybody, and we'll talk next week. Cheers now.
Perfect.
Bye.
All right. Thank you. Thanks. Bye now.